Why do bridges collapse or the metal components during forging fail? Or for that matter, why do the ground, which is underneath a big building, sometimes give in? So the answer to all this is not in the language of the easy world of elasticity, which only provides the mechanisms of reversible deformation. It is in the theory of plasticity with irreversible deformation. Hello everyone, welcome to this NPTEL course on Advanced Plasticity of Solid Continua. I am Professor Debashish Roy from the Department of Civil Engineering, Indian Institute of Science, Bangalore. If you put a sufficiently large loading on an engineered structure or a physical system, it undergoes irreversible plastic deformation that remains even after the loading is removed. The system never reaches back its original configuration. So to understand and be able to model these plastic deformation in a trustworthy manner lies clearly at the heart of efficient and modern design practices. But the modern treatises that are available mostly talk of plasticity as a theory consisting of a jumbled set of rules and empirical formulas without looking into the underlying scientific thread that binds the different models. And this is where this course takes a more modern perspective. So in this course, we move beyond this recipe approach and make explicit the underlying mathematical principle that informs all the different models that you see in practice in any course on plasticity. In the process, we make use of the language of convex analysis and incremental variational methods to derive all the different methods together. So in this sense, it's basically a unified principle that we lay out for you to ensure that you understand it once and for all and in a proper manner. The thing here is that we start assuming that you have not a lot of background in the continuum mechanics of solids with the basic kinematics and kinetics, and then move on to the balance laws. Then onwards, we move on to the thermodynamics, especially the thermodynamic closure leading to the constitutive relations. And then especially we explicate on the Coleman-Knoll principle, and then we actually start using the language of convex analysis to deal with different types of plasticity. Rate independent plasticity to start with, then rate dependent plasticity of different kinds, including the Perzina type. Then we move on to the strain gradient plasticity and other plasticity models, for example, plasticity under large deformation. So what is there in this course for a student or a practitioner? If you are an early career PhD student or an MTech, advanced MTech student, then you would learn from this course the mathematical rigor needed to get a head start in your research. On the other hand, if you are from the industry working with advanced FES software tools, implementing certain additional interface codes for yourself, then this course will help unmask what you have probably looked upon as a black box so far. And also it will help you write algorithms for yourself which will converge quadratically fast. So I invite you to join me in this exciting journey to the heart of materials genome, which is to understand the mechanics and physics of plastic deformation in this NPTEL course. And you need to enroll for this course online in the NPTEL website so that we can get you begin on your journey of curious search for the scientific facts that inform plasticity. Thank you.